Welcome back. I'm Larry Atherton from Motion Software. And a special hello to our new subscribers. I really look forward to exploring internal combustion engine and simulation technology with all of you. This is the third video in this series and a second deep dive into camshafts. In the previous CAMSHAFTS.1 video, we provided an in-depth look at the essentials you need to know to understand and use performance camshafts. If you didn't see that video, give it a quick look. I'm sure you'll find it helpful when trying to decipher the wide variety of published cam specs. And you'll even learn how to read between the lines on cam cards to model any cam from any manufacturer. Up to now, we have analyzed and simulated 3 cams using data supplied on cam cards, which are paper tags tossed into the box with the camshaft that provide cam specs and installation information. We modeled these camshafts in an engine simulation and rated the cam cards for accuracy and completeness. In this video, we'll work with 3 more cams that each present their own twists in data entry. This will be an interesting and useful video for anyone who works with stock or performance IC engines. Let's start off with a real door rattler and build a 1968 427 big block installed in an early Corvette. This L88 engine option was available from the factory, but only about 300 were delivered to dealers. Remarkably, one recently sold at auction for more than $3 million. We'll be using this Crowler Cam's roller flat tappet profile designed for 396 to 454 Chevy big blocks. I've pre-built this L88 in DynoSim 6 minus cam specs that we'll use for data entry and testing. A good place to begin our simulation is to first enter lobe lift specs. The lobe lift values are provided on the cam card in the box titled Timing Events. We'll start by entering 437 thousandths for the intake and 428 thousandths on the exhaust side. Next is rocker ratio. It is clearly indicated as 1.7 for both the intake and exhaust rockers. Notice gross lift has been calculated. This is the lift measured at the valve with 0 lash. A quick check confirms our gross lift value matches the cam card. Keep in mind that most cam cards and other sources of cam data display valve lift as a gross lift spec with 0 lash. Since this is a flat tappet camshaft, we'll enter valve lash for both valves, 18 thousandths for the intake and 20 thousandths for the exhaust. The true lift at valve heights are now displayed. These values are also known as net lift, which is the actual lift at the valve. Next, we'll enter the primary valve event timing that pinpoints when the valves open and close, marking the start and end of mass flow in each cylinder. And we also need secondary lobe timing events, as this data helps model the shape and acceleration rates of the cam lobes. A quick look at the cam card shows that secondary timing is measured at 50 thousandth inch lifter rise, which is the most common secondary timing lift height. Unfortunately, the primary timing lift height does not seem to be included on the cam card. Many flat tappet cams use 20 thousandth inch lobe lift for primary timing. And to be sure that this was also the case with this Crowler cam, I confirmed it with a quick call to the Crowler tech line. But before entering these timing values, remember that in order to perform the engine simulation, we need primary event timing at 6 thousandth inch valve rise. That's when flow actually starts and stops in the ports, not 20 thousandth inch lobe lift as provided on the cam card. We'll use the multi-standard lift calculator again to convert timing values to the needed 6 thousandth inch lift specs. I'll enter primary lift of 20 thousandth inch and the secondary lift of 50 thousandth inch. The primary duration values are 311 and 321 degrees at 20 thousandths lobe lift, and 278 and 287 degrees for 50 thousandth inch lobe lift. But the calculator also needs the intake and exhaust center lines, so we'll enter those here. The intake center line of 106 is shown here on the cam card, but as is usually the case, the exhaust center line is not provided. We can easily calculate it using the equation exhaust centerline equals 2 times the lobe centerline angle minus the intake centerline angle. The result is 114 degrees. Now, the multi-lift calculator displays the original cam specs and the calculated SAE timing needed to model the cam in DynoSim 6. Press the Use button to transfer these values to the simulation. Before we continue our cam card analysis, I want to take a minute or so to address a viewer's question about the multi-lift calculator. He wanted to know exactly what the calculator does and how the results are used in the simulation. Here is the intake lobe lift curve drawn from the information provided on the Crowler cam card. The curve starts and stops at 20,000th inch lifter rise, since no data is provided for lift below these points. These missing parts of the lift curves are not only needed to determine 6,000th inch valve timing, but they are also used to improve lift curve modeling all the way to max lift. Here is the derived intake lift curve from the multi-lift calculator. Notice how opening and closing ramps have been added, along with 6,000th inch timing points. In addition, these ramps have been extrapolated to reshape the entire lift curve. So the multi-lift calculator allows reconstructing and extending ramp data that produces a more accurate model of the original cam design. Okay, back to the Crowler cam card. Another area of possible confusion on the Crowler card is this note that indicates the cam has 4 degrees of advance ground into it when it was manufactured. This seems to mean that the timing specs on the card already include a 4-degree advance. To confirm this, add the 50,000th lift intake opening and closing points, then add an additional 180 degrees, divide by 2, and subtract the opening value. This will give you the intake centerline. Use the same technique for the exhaust, except subtract the closing value rather than the opening point value. You should get 106 degrees for the intake and 114 for the exhaust. This confirms that all timing specs on the cam card reflect the built-in 4-degree advance. If they didn't, the calculated centerline values would be 110 degrees for both intake and exhaust. Just as a side note, 4 degrees of advance is sometimes used to help compensate for new timing chain stretch, the most of which can happen surprisingly within the first few hours of engine operation. Now that all cam specs have been entered into the simulation, engine performance is displayed. With this setup, the L88 produces a solid 560 horsepower at 6,200 RPM, enough to give an awesome street ride. Here's a quick look at how this engine was modeled in DynoSim 6. Basic L88 engine data was available online from several great web resources, including the extensive flow data provided at the Stan Weiss website, links included below. While not the OEM cam for this engine, I chose the Crowler 01523 because the timing is similar and the cam card was readily available. This engine used an 850 CFM Holley carburetor, the largest ever offered on a production GM vehicle. Ignition timing was set at 25 degrees on the crank, with 1.5 degrees advance per 1,000 RPM, with the advance stopping at 3,000 RPM. Total advance is about 30 degrees. While this timing worked well in the simulation, optimum ignition timing should always be carefully tested to avoid detonation, especially on engines with high compression ratios like this one. The fuel selected for the simulation was high-performance gasoline, and the factory compression ratio of 12.5 was used. If this project engine was actually built today, I would recommend that it only run leaded racing gasoline. Valve sizes are two 18-inch intakes and one 84-inch exhaust. Peak intake flow is 302 CFM, and exhaust peaks at 208 CFM, both at 700,000th inch valve lift. All measurements were recorded at a pressure drop of 28 inches of water. Finally, 2-inch exhaust headers were tuned for 6,600 RPM at a length of 30.5 inches. Primary pipes merged at a 4-inch diameter collector 19.5 inches long. Okay, let's review how helpful this cam card was in building our simulation model. 1. First of all, the graphics and layout were clear and informative. 2. The primary duration specs, however, were not very well documented. I had to call the Crower tech line to get the final word. If the card had simply stated, all primary cam specs are based on 20,000th inch lobe lift with zero lash and a rocker ratio of 1.7:1, it would have been clear and eliminated a bit of head scratching. 3. In addition, the cam card also indicates 4 degrees of advance were ground into it when manufactured. At first read, it was not clear to me if this advance was included in the cam specs on the card, or if all the specs should be advanced 4 degrees to properly model the camshaft. But by calculating the center lines from 50,000th inch timing values, I was able to confirm that all cam card timing includes 4 degrees of advance. 4. Finally, the Crower card clearly indicated that 50,000th inch secondary timing is measured at lift arise. This is the SAE standard, and it's important information that I'm happy to see included. The bottom line, some of the basic information needed to model this cam was not clearly stated, and as is the case with most cam cards, the primary valve lift specs were given at zero lash. Without a mention of this on the card, I'm sure that some enthusiasts may not realize the actual valve lift with this cam in a running engine. Now let's switch gears and model something at the other end of the spectrum. This cam is designed for a race-ready Fiat 128 4-cylinder single overhead cam engine. The cam is manufactured by CAMSHAFTS, a Belgian company. They are well known for performance valve-train components for IC engines. Let's review their cam card specs and compare them to the American manufacturers we've analyzed up to now. Again, I've pre-built the Fiat 128 in DynoSim 6, minus cam specs, that we'll use for data entry and testing. First, we'll enter lobe lift values. This cam card uses metric units, so I've set DynoSim 6 to display metric values for components, while keeping results in horsepower and torque in pound-feet. This units option in the simulation is popular with European engine builders. The lobe lift at peak height is 14.5 millimeters for both the intake and exhaust lobes. Notice that the valve lift height is also 14.5 millimeters, indicating that this engine either does not use rocker arms or the rocker ratio is 1:1. Finally, the maximum recommended lash is 0.2 millimeters for both the intake and exhaust valves. Now let's look into cam spec checking heights. CAMS uses lift heights of 0.1 millimeter for primary timing and 1.0 millimeters for secondary timing. This seems to be common for European cams. These metric lift values are equal to 3.9 thousandths lift for primary valve timing and 39 thousandths inch lift for secondary timing. We'll use the multi-lift calculator to derive equivalent SAE values. Before starting the calculator, enter the required intake and exhaust center lines of 104 degrees. Now select 0.1 millimeter lift for the primary lift height and 1.0 millimeter for the secondary lift height in the calculator. Enter the primary duration of 326 for intake and exhaust, then enter the secondary duration of 288 for both valves. Press the Use button to transfer these timing values to the simulation. With all data entered, the simulation indicates this popular 1.1-liter engine should produce about 150 horsepower at 9,000 RPM. Not bad for a small 2-valve per cylinder engine. Looking back at the cam card, notice that CAMS provided additional valve lift data that we can use to check our cam timing at top dead center during valve overlap. Before we proceed, also note that the cam card indicates peak valve lift and valve lift at TDC are both measured at zero lash. So it's essential that we set the lash back to zero to properly perform this overlap validation test. I'll modify this window to display valve lift curves. Right-click to assign lift data to the Y1 and Y2 axes. I'll set exhaust lift to the left and intake lift to the right. Finally, I can optimize graph scaling for the best readability. Here is TDC, and notice how both valves are open during overlap. If we move the reticle line to TDC, we can view valve lift directly from the sim data pop-up window. The measured intake lift is 6.597 millimeters, and the exhaust is 6.712 millimeters. The exhaust lift is a near-perfect match to the CAT-CAM's 6.7 millimeter lift spec, but the intake is off by 0.25 millimeters, or about 1.7 degrees retarded. This slight mismatch will make very little difference in the simulation, but we can correct it by adding 1.7 degrees of advance to the intake centerline. Now the lift values match within 0.01 millimeters, which is about 4/10,000ths of an inch. After returning lash back to 0.2 millimeters, we can measure the change in predicted power from 151 to 152. That was a pretty deep dive into this CAM card. How do you think we should rank it in completeness and ease of use? First of all, I believe the overall layout and graphics were clear and easy to read. The lift curves show how duration and valve timing are measured, and even include additional valve lift heights for reference. Second, the CAM card indicated that the lift height used for primary timing was 0.1 millimeters. And while the card didn't indicate if this was valve or lobe lift, in this case it doesn't matter, since the rocker ratio is 1:1 on this engine. Secondary timing is 1.0 millimeters, a common secondary metric timing standard. Third, the primary valve timing events at 0.1 millimeter lift were not provided. That's understandable, since their customers would not use these values during CAM installation. But for simulation purposes, these specs would have added valuable data to confirm our calculations. Finally, the additional valve lift at TDC spec was a great way to confirm CAM timing and installation accuracy. It can even be more accurate than the 50,000th inch lift US standard, since in this case, lift heights at TDC are more than 200,000th inch up the lobes. In summary, this CAM card is quite clear and complete. The only negative thing I can say is, I wish the type was larger to make it easier on my older eyes. That and not including primary valve event timing are my only complaints. Our final CAM card is not a card at all. Instead, it's an electronic version of the traditional paper card. While this one may be in the cloud, it's readily available from the Summit Racing website, where you can view and print a copy of your own. This camshaft is designed for single or twin turbocharged Gen 3 small block Chevys. Unlike earlier turbocams with minimal valve overlap that helps restrict exhaust gases from spoiling the intake charge, this grind utilizes more overlap to optimize performance when combined with new, free-flowing turbine housings used on modern turbochargers. The CAM is a hydraulic roller lifter design with a recommended speed range of 4,000 to 7,500 RPM. The Summit card is packed with information and well organized. Let's use this data to begin entering lobe lift specs. Intake lobe lift is clearly indicated as 368 thousandths, and exhaust is 356. This is measured at 0 lash. Rocker ratios are 1.7:1. And since this is a hydraulic lifter cam, running lash is 0. A quick check confirms that valve lift matches the CAM card at 625 and 605 thousandths. This CAM uses the SAE standards of 6,000th inch for primary lift height and 50,000th inch for secondary lift. So we can directly enter valve timing into the simulation. The multi-lift calculator isn't required. The primary timing points are 34, 77, 90, and 27. The secondary timing is 10, 51, 65, and 3. With all data entered, DynoSim 6 completes the LS1 simulation that includes a twin-turbo induction system. With about 14 psi of boost, the engine reaches a peak of 900 horsepower with torque ranging from 600 to 700 pound-feet at 4,000 to 7,000 RPM. To say this would make an awesome street rod would be an understatement. Now, let's review how well the Summit Cam card provided the information we needed to complete the simulation. 1. This card was well organized and packed with information, although lacking cam timing graphics. 2. Both primary and secondary lift heights and timing events were included. The card clearly stated that all lift values were based on zero lash measurements. It also included the lobe centerline angle and intake and exhaust center lines. 3. The SAE standards for valve timing were used, making simulation data entry easier. 4. Primary and secondary duration values were also included, making it easy to cross-check valve timing events. 5. One minor nitpick is while the card stated the cam was manufactured with 5 degrees of built-in advance, I would have liked to have seen a note specifically stating that all specifications on this cam card include 5 degrees of advance. In summary, this cam card was nearly perfect. My thanks go to Summit for trying just a bit harder than the other guys. In the last 2 videos, we've worked with 6 cam cards, ranging from easy to use to downright tricky. I hope the information we've covered makes you more comfortable analyzing cam card data. If you have any questions, shout them out in the comments. And if you have a specific cam card that you would like to see modeled, send a clear photo or PDF to support@motionsoftware.com and we'll share it in an upcoming video. The next video will introduce more cam tech, and you'll find out how it's possible to test a range of cams automatically in the simulation. We'll also dig deeper into data entry and introduce more simulation tech. I know you've heard it before, but please like and subscribe to keep the tech information coming. We'll end with some camshaft insights from David Vizard, who gained his knowledge from years of racing minis and building countless small block Chevy hot rods. See you next time.
The exhaust system on a modern high-performance engine is an incredibly complex subject, but to have a halfway understanding of exhaust is really important if you're dedicated towards making horsepower from your engine. But let's consider a road car, right? Let's say you have an optimal exhaust manifold. You then have to put a muffler or silencer on it. Is this going to cost power? There is a misconception that no matter what you do, a silencer or muffler is going to detract from the capability of the exhaust. This not need be so. How's this doable? Well, the first thing is you have to look at the exhaust system as 2 fundamentally separate things. There's the exhaust manifold that creates the pressure waves that extract the combustion chamber charge and induce the fresh intake charge. Then there is the part of the system which must suppress noise. If we deal with them separately, we can actually build a system that has 0 effect on horsepower. Here's what you do. First off, you make sure that the exhaust dumps into a resonator box which is of large volume, at least 10, 12 times the volume of one cylinder. If you then have the resonator box dumping into a muffler that flows at least 2.2 CFM for every horsepower the engine can make on an open exhaust, the engine will not know the mufflers are there. So, by having the expansion box or the resonator chamber and a muffler with 2.2 CFM per horsepower or more, we have got a system which is invisible to the engine. Result, 0 change in power.